All right. So we have the second lecture. And so yesterday I talked about surfaces. So to have a better blackboard skills, let me do this first. Not really? Okay. Okay, so let me recall quickly. So we looked at the groupoid, Birmori of P2. Thank you. Okay. So we had the groupoid Birmori of P2, and I gave you two constructions of groupoid homomorphisms. So with one, we went to a free product of Z modulo 2, where we used the Bertin involutions. And in a second construction, we went to a direct sum of Z modulo 2, where we used the Sarkisov links between Hirzebruch surfaces. And how we did the construction was, so we had a set of generators and relations of this groupoid. And so the groupoid, so the objects are rank 1 fibrations. Generators are birational maps between rank 1 fibrations that are dominated by a rank 1 or rank 2 fibration. So either isomorphisms of Mori fiber spaces or Sarkisov links. And like to take up a comment by Serge from yesterday, or maybe joint comment of Serge and Stefan. The relations, so I called them trivial relations and elementary relations. And another way to say it is that, so here we take the relations such that, let me write it down. So let's say chi1 up to chi n, a relation such that there exists a rank 1, 2, or 3 fibration that dominates each of these birational maps involved. Dominating. Each chi I. So where chi I is either a Sarkisov links or a isomorphism of Mori fiber spaces. Okay? So I had the trivial relations, so I had two kinds of trivial relations. They correspond to these relations coming from rank 1 or 2 fibrations, and the elementary relations are then these rank 3 fibrations. Okay, I just wanted to get this out. And so the rank R fibrations were the important notion, and I want to just quickly recall. So we have that X over spec K is a rank R fibration exactly if X is a Del Pezzo surface of pica rank R. So this comes directly out of the definition of a rank R fibration if we take the base to be spec K. So I want to do one quick other construction in the surface case. So, and this is going to be with Severi-Brauer surfaces. a Severi-Brouwer surface, let's say maybe a non-trivial surface S over some field K okay, so let me do, let's say S is a non-trivial Severi-Brouwer surface over K, which means, so that is S base change to the algebraic closure is isomorphic to P2 over the algebraic closure, but so with no rational points. Okay, so this is what it means to be a non-trivial Severi-Brouwer surface. Okay, so we have such surfaces which are geometrically P2, but over the field they are not P2. So this is maybe a bit strange, but like I just want to emphasize one fact. So there is a lot to say about such surfaces, but I don't want to say much. So the only fact I want to mention is that if P is a point on S, then 3 divides the degree of the point. This is the only fact I want to mention. Because now let's look at whether we can construct a groupoid homomorphism. Okay, so this is the idea. And so let's first look at the Sarkisov links that we can have, okay? So what can we do? So we start with S, our non-trivial Severi-Brouwer surface. And so what can we do? So this is a Mori fiber space over spec K. So now we want to construct a rank 2 fibration. So what we have to do is we need to blow up a point. So what kind of points do we have? Well, the degree of every point is divisible by 3. So let's take a point of degree 3 and let's blow it up. So now we go to a Del Pezzo surface of degree 6. And so geometrically S is P2, right? So geometrically we blow up 3 points in general position. And now in fact, so we have the 3 lines through the 3 points, and they still form a Galois orbit over our field K. So this means that we can contract it. And now another fact is that we will go back, so we will go down to a Del Pezzo surface of degree 9, but it doesn't have any points. But in fact, this is not the same surface as in the beginning, but it is the opposite Severi-Brouwer surface. So this is also a fact. So here S op is the opposite Severi-Brouwer surface. Yes? Yes. So for point of degree 3, there is no condition. So there always exists a point of degree 3. Yes. Yes, so if you have a non-trivial Severi-Brouwer surface, there always exists 1 point of degree 3, and in fact, there always exist at least 2 points of degree 3. This is, yeah. But in general, I think it's hard to know, who exists, yeah, how many points. So, okay. Sorry? Yes, so by miracle, points of degree 3 are always in general position on a non-trivial Severi-Brouwer. And the reason, yes, exactly, yes. And in fact, this is it is immediate, because if they would be on a line, we would have the line through the 3 points, and this would be Galois invariant. So this, because, yeah, okay. So the line is defined over K, which means it is a P1, so it has rational points. It's really a P1 over K, yes. Yes, yeah. Yes, and we don't have any rational points, so yeah. So points of degree 3 are always in general position. Okay, and now here, this gives a birational map, and so this is a rank 2 vibration. So the opposite, so one can look at Severi-Brauer surfaces in terms of central simple algebras. I'm not sure. Maybe. Okay, so this is a rank 2 vibration. So this is a Sarkisov links. Okay, so it is rank 2 because Y6 is del Pezzo, because we blew up points in general position, and the pica rank is 2, because S has pica rank 2, and so Y6 has pica rank 2. And okay, good. Now what else can we do? We have also, okay, so points of degree 3, so the next point is of degree 6. So we can do S. So we blow up a point of degree 6, we go to a cubic surface, Y3. And now again, geometrically, what we do is we blow up 6 points on P2. And so now we have the 6 conics that go through 5 of the points. Okay? So we take 5 of the 6 points, there is a unique conic through it, and we do this for every subset of 5 points. And in this way, we get the curves that we can contract. So again, we get 6 curves that we can contract. Because again, one can check that these orbits of -1, so that this, like the -1 curves that come from these conics, they are again a Galois orbit. And by miracle, we go back to S op. And so this again, over spec K, this is a Sarkisov link. Now, do we have any other Sarkisov links? So the next point that we could blow up is of degree 9, right? But degree 9, if we blow it up, it's not del Pezzo anymore. So this won't be a Sarkisov link. Okay, so what else can we do? Now we need to look at all the new surfaces that were created with a Sarkisov link. And we need to check what kind of Sarkisov links start from there. Okay? But I mean, so now S op is again a non-trivial Severi-Brauer surface. And so the types of links that it has is like the same 2 types of links. Okay? So this is to say that these are all Sarkisov links that exist in Birmori. Okay, so now let's look at rank 3 vibrations that dominate these links. Okay? So let's first look at the case here, the 6-6. So what can we do? So what we need to do is, to get a rank 3 vibration, we need to blow up a point on Y3. Okay? So what kind of point can we blow up? So again, the degree of the point is, the smallest degree is 3. So let's blow up a point of degree 3. Okay, but then again, we are not del Pezzo anymore. So because here we have a cubic surface, so I can't blow up a point of degree 3 and still be del Pezzo. So with this means that this link is not involved in any rank 3 vibration. So here, there is no rank 3 vibration dominating. So maybe let me call this alpha p, where p is the point that we blow up, and beta p, dominating beta p. Now let's look at alpha p. So here we blew up a point of degree 3. So let's look at the rank 3 vibrations that dominate the link. So what we can do is we blow up a point of y6, on y6. So what can we do? Smallest degree is 3. Let's blow up a point of degree 3. And then we get a cubic surface. Cubic del pezzo, so this is actually possible. So there are rank 3, there are rank 3 vibrations dominating these links. Let me quickly. And what you get is this. So I don't want to do it, and I think you won't see it, but you can take a look afterwards. So we get a hexagon. So now here, so every face corresponds to a Sarkisov link. And so we have 6 Sarkisov links involved in the rank 3 vibration in the center. And in fact, what we get is that, in fact, so the points that we blow up with the 3 ones, okay, let me maybe. So the Sarkisov links that are here, here, and here, they in fact, the points that we blow up in each of them, they have the same residue field. And just to say that in fact these will turn out to be equivalent. And in this way, in fact, we get something with a 3 torsion. We are obliged to use a 3 torsion. Okay, but sorry, I don't want to say much. So let me just write down the groupoid homomorphism that we get. So we get Biamori S going to, so we have a free product of Z coming from the links where we blow up points of degree 6, right? Because there are no elementary relations involved. And free product with the links coming from the points of degree 3. And here we will get the Z modulus 3. So there is a bit more to say about the hexagon and how we get this exactly. But what I want to say here is that we do get this Z and the Z modulus 3. So this is just like different to the constructions I showed you yesterday, right, where we always had the Z mod 2. Okay, so now I would like to mention some open questions, because if I do this in the end, then I won't have time for it. So. No, this is too big, no? Okay, so the open questions. So the first one is about the Cremona group over C of rank 3, so for 3 folds. And the question is the group generated by elements of finite order? And just to say, like, the answer is, so if n, so if the rank is 2, then the answer is yes. And if n is at least 4, then the answer is no, by the theorem of Lin and Schindler that I mentioned yesterday. Okay, so dimension 3 is the remaining case. Now, in fact, it's also like, so this is like a specific generating set, but it would also be interesting to know, like, I know a generating set of elements that satisfy some property. Okay. So here I chose the property of a finite order, elements of finite order, but it's also interesting to know, like, some other description of elements that generate. Okay. Because as I also mentioned yesterday, like these group homomorphisms, they are also always in some kind of a negative result, right? In the sense that the elements that lie in the kernel, they do not generate the whole group. So it would be nice to have like some positive thing, or also like, yeah, to know what does not. Okay, and the second question is about the abelianization. Of a Cremona group, so again complex. Let's say for n at least 3. And so the question is, like, for which p does there exist to me, it's completely open. I don't. So I know when people ask me these questions, sometimes I say yes and sometimes I say no, but it's really, I guess it depends on my mood or something. So the question is, for which p does there exist p torsion in Cremona n over k. And so what we know is that, so for p equal 2, it exists, so yes. And this is for n at least 3. And this is due to Blanc, Lamy, Zimmermann, BLZ. And for p equals 3, the answer is also yes. But here we only know it for n at least 4. And thank you. Yes, up. Yeah, sure, yeah. Yeah. Okay, so here we know it for n at least 4, and this is of the work with Blanc and Jasinski. And in fact, the 3 torsion, it has a, well, it comes from this part here. This is a, I don't know, a 70 pages paper in 2 seconds. Okay, so this is what I wanted to mention here. Okay, so now I want to go finally to higher dimensions. So I will give you the definition of a rank R fibration for higher dimensions over the complex numbers. So definition, so now we take n, okay, at least 2, but the interesting is higher dimensions, and k equals c. So now a surjective morphism high from x to b with connected fibers. Yes, so here I do it for C, yes. Thank you. Let's put C. I mean, of course, one can ask the question over any field, and it would be interesting, but let's take with C. Thanks. with connected fibers. Dimension of X strictly larger than the dimension of B is a rank R vibration. If so, X over B is Q factorial terminal Mori dream space. Mori dream space. And what else? So I want the relative pica rank X over B is equal to R, and then some technical details. Okay, so in fact, we will not really use the definition as I write it down here for the rest of the talk. Okay. But I just want to mention a few things. So first of all, so Q factorial. We use this so that we can use intersection theory. That's why we want it. Terminal, these are some kind of a mild singularities, and one has to allow these singularities when one runs the minimal modal program. So even if you start with some smooth variety, you need to allow terminal singularities for that it's possible that it works. And Mori dream space. So this is, so if we have this, then one can run any MMP, and one gets only finitely many outputs. So this is a dream space in the sense of a minimal modal program. So like everything works very nicely. And one of the technical details is, in fact, we want something which is even better. So one of the techniques is that we want that any output of an MMP that you run is again Q factorial terminal. This is a strong condition. And yes. And so in this sense, I would like to make a comparison with like Del Pezzo surfaces, right? Because a Del Pezzo surface is very nice with respect to contracting -1 curves. So every curve that you can contract, you get a smooth surface. This is very nice. And so in this sense, like also here, if we do any contraction that we do in the MMP setting, we also get something which is very nice, so Q factorial terminal. So there are some more things, but okay, that's enough. Okay, so now a remark. So now again, rank 1 vibration will be Mori fiber spaces, rank 2 vibrations will be Sarkisov links, and rank 3 vibrations, they will be these elementary relations. So now the Sarkisov program is basically like conceptually the same as in dimension 2 with these rank R vibrations. So now, so what is, so if we have Y over B a rank 2 vibration, we get the following diagram. So I have Y over B. And now in higher dimensions, we need to allow some pseudo-isomorphisms. So when I do dots, it means pseudo-isomorphism. Okay, so now here we start with this rank 2 vibration. We have 2 rays that we can contract, and this will give us such a diagram. And such that here we have a Mori fiber space. So any birational map between two Mori fiber spaces that satisfies such a diagram is a Sarkisov link. So now we want to find some Sarkisov links where we can control the relation so that we can construct a group homomorphism. Okay? So, and the links that we will choose will always be of type 2. So let me remind you what this is. May I? So this is when we have that all the bases are isomorphic. So we have the following diagram. We have x1, y1, y2, x2. So maybe if, so this here is my link chi. Sorry, so what I wanted was things of type 2, so we have the base. And let me maybe denote the base with a b chi, if chi is the link. Okay, so this is a link of type 2. And let me use some notation. So now here we have a divisorial contractions. And in here, let me write the gamma 1 for the center of this contraction. And in here, gamma 2. So I have a gamma I inside of xi, the center of the divisorial contraction yi to xi. And so now I'm interested in the generic fiber of these, so here we have Mori fiber space. So the generic fiber Si of xi over b, so over b chi. This is a variety over the function field of the base. Is over the function field of the base. And the dimension of the generic fiber is the relative dimension of xi over the base. And so this birational map chi and chi induces a birational map between the generic fibers. So from S1 to S2. So this is now over. So this is now over this function field. Okay. And okay. And in fact, one can show that since chi is a Sarkisov link, so these conditions here, they imply that the induced map here is either an isomorphism or it is a Sarkisov link. And I should mention that this is for in the case when so at least when the generic fiber has dimension 2. Okay? Because, okay, so this is going to be, yes, please. So one can make like, okay, so I don't think, it doesn't have to be smooth, but I mean, then you can like make a resolution run MMP, and then, yeah, you have to work, and at least in the cases that we use, you can always get like a Mori fiber spaces with a certain generic fiber, which is so that X over B is a terminal Q factorial and everything, and that the generic fiber is smooth. So okay, so I was speaking of dimension 2. So okay, sorry, what I said was when the generic fiber has dimension 2. Okay, and so now what was your question? Sorry. Yes. Because so because of the relative pica rank. So here you have relative pica rank 1. So the generic fiber is going to be a surface of pica rank 1 over the base, over the function field of the base. Yeah? Yes, exactly, yes. So can you repeat again? So you look at each fiber, and yes? Yes? Yeah. Yes, yes, yes. Yes, sir. Was I saying general all the time? Did I say general? Generic, okay, good, good. Yeah, generic, okay, good. No, thanks. Okay, so what are the known constructions? Okay, so again, so the goal is that we want to find links of type 2, where we can control the elementary relations in which they appear. Okay, and so the known constructions are the following. So first of all, the very first construction that we had in higher dimension, this used when the relative dimension, so when the generic fiber Si has dimension equal to 1. So these are the conic bundles. And this was a construction done by Blanc, Lamy, Zimmermann. So here we have conic bundles. Okay, then we have constructions where the generic fiber has dimension 2. And these are constructions by Blanc and Jasinski, and also the construction with Blanc and Jasinski. And there is also a construction in where the generic fiber has dimension 3, and this is due to Zikas. And so in fact, so maybe this is a bit more complicated, but so he does dimension 3, okay? So he just, so he does a 3 folds over spec C. Okay, so his links are when here we have a spec C. And so afterwards I would like to focus on the dimension 2 case. But first let me say like some idea of how one can control the relations of such links, or like how people manage to control the relations. So first of all, the one by Zikas. So what he does is he finds gamma, so gamma I, so the centers of the blow-ups of the divisorial contractions with very specific genus and degree. With specific, so genus and degree. So right, so now the gamma I is a curve in his case. Okay. Yes, curve in P3. With specific genus and degree, and so he has like several values for which his construction works, and so I only noted down 2 of them. So 2,8, for example, and 14,11, and there are some others in between. So yeah, some specific values, and so somehow the idea is here like that he blows up this curve, which is in somehow like so that genus and degree are like still small enough so that you get a rank 2 vibration, so that you get a Sarkisov link. But it is also large enough such that you do not have any elementary relation involved in the link. So, and in his case, no elementary relation involved. Okay, so also this construction is quite explicit. So it is a nice construction. Okay, then in the other 2 cases, so dimension 1 and 2 of the generic fibers. Okay, so if maybe, okay, let's maybe do BLZ, BY, BSY. So generic fiber has dimension 1 or 2. Then, so to bound relations, so we take only links chi, with such that the gamma I, so the centers of the blow-ups, have large covering gonality or genus. So gonality is in the construction of BLZ, or in other words, in relative dimension 1. And the others, so BY, BSY, we take large covering genus. So, okay, in fact, so BY, they also do it for three folds. And so there, the covering genus is just the genus of the curve that they blow up. So we take this. So you think of a covering genus or gonality as like some complexity of the link. So we want to have this the center of the divisorial contraction. We want it to be complicated enough. So what are now the links that we actually take for the generic, when the generic fiber is a surface? So in Blanc-Jasinski, we have, dimension of the base of the link is 1, so this is a curve. And we have dimension of the variety is 3. And what they take is they take such that the generic fiber Si is a Del Pezzo surface of degree 3. And such that the induced link between these Del Pezzo surfaces of the degree 3 is as follows. Namely, such that so the generic fiber, they blow up a point of degree 2, and they go to a Del Pezzo surface of degree 1. And then there we have again the Bertini involution that I mentioned yesterday for birational maps from P2 to P2. And so we contract the point of degree 2. So I want to draw a picture. So I draw x over b. So let's say x1 over b. So the center looks something like this. So it is a curve. this is the gamma. And so on the generic fiber, you blow up a point of degree 2, you get this del pezzo surface of degree 1, and you contract. So they also call these links Bertini type. And so they, okay, so gamma has a large genus. Okay. And maybe a remark here. I mean, one could do, like if one wants to use like a link where we have a del pezzo surface of degree 1 on top, one could also think like, okay, maybe let's take here del pezzo surfaces of degree 2. Right? On del pezzo surface of degree 2, we can blow up a point. Del pezzo of degree 1, we can contract again with the Bertini involution. Okay? But now what happens now, if we blow up just a point of degree 1, then the curve that we have here is a section. Okay? But now if we have a section, then the genus of this curve has the same genus as the base. So in this way, we cannot have a large genus. Okay. Okay, so this is the construction of Blanc-Jasinski. And now, with Blanc and Jasinski, we use the following types. Now we take SI non-trivial Severi-Brouwer surfaces. Such that the induced birational map S1 to S2 is a Sarkisov link. So now a Sarkisov link between these surfaces. Those linkers, let's say, over the of the base. Yeah. And so in fact, we will take the base to be, sorry. So we do this for n at least 4. We take the base to be p n minus 2. So here I can write the p n minus 2. And now a remark here. So here I say I take n at least 4. Okay, but I mean I could do it also for n equals 3. I could take a 3-fold and then I would take p1. Right? So I mean, so far nothing, there's no problem. But the thing is, if the base is a curve, then over this field, so y n at least 4. Because if the base is a curve, there are no non-trivial Severi-Brouwer surfaces. Okay, so this is like an arithmetic statement. You have the function field of a curve, then we do not have any non-trivial Severi-Brouwer surfaces. This is why our strategy only works for dimension at least 4. Okay, so here, before I just said that to bound the relation, we take a large, no, sorry, so this is like not a full sentence. So here I should have mentioned covering gonality or genus large. Large. And so so what do I mean? So maybe, so remark, if covering genus or gonality of the center that we blow up, covering genus, is large, then we have that any rank 3 vibration P over B that dominates the link the link, so chi, has that the dimension of the base is equal to the dimension of the base of the link. And so this is not a remark, this is like not obvious at all because it uses a boundedness of a Fano varieties. So this uses boundedness of Fano. So this is known as the BAB conjecture, which is a theorem by Birka. Okay, so, yes. Yes. Yeah, no, I didn't say it. Thank you. So covering gonality means that. So we have the covering gonality of a gamma means that there exists an open dense subset of gamma such that every point on this open subset has a curve of the gonality, at most this one, that goes through the point. Okay. Now I'm really afraid that I will go over time, but okay, it's still okay. Yeah, and so, okay. So in this way, this sense, I meant like we can bound the relations in which the link appears. So we have a bound on the base of on the dimension of the base. And here I also want to again mention Zika's work. He does not use this huge result. Okay? So his construction works really like much more explicitly, and yeah, no need for this here. Okay, so with the Okay, so now I want to state one last theorem where we go, so we discuss again like the group homomorphisms. And I want to, the theorem will tell you that when we have a group homomorphism on the generic fiber, it will extend to a group homomorphism on the higher dimensional groupoid, so on Biomori X. So theorem. So, okay, let's take X over B Mori fiber space with generic fiber S, del Pezzo surface over the function field of the base. And now I make one assumption. Assume that S is not birational to any conic bundle. So to a conic bundle. So this notion also is a notion of a birational solidity. I make this assumption and then there exists an integer G at least 1 depending only on the dimension of X. Such that the following holds. Okay, so the theorem is not over, it will continue. Okay, so let's say we have a groupoid homomorphism on the generic fiber. So assume there exists eta from Biomori S to G, groupoid homomorphism. Such that, okay, so if phi and phi prime are elements in Biomori S that are weakly equivalent, so I didn't say what this is, that are weakly equivalent. So basically, weakly equivalent, yeah, okay, yeah. Then we have that eta of phi is equal to eta p prime. So, I mean, okay, so for the purpose now, let's just forget about the weakly equivalence, just the equivalence that I gave you last time. So, yeah, I don't want to be more technical. Okay, so we just want that if they are equivalent, that they have the same image under this groupoid homomorphism. And we also want that if phi is induced from a Sarkisov link, which has so of covering genus small, so of covering genus smaller or equal to G. So that this is the then it is sent onto the trivial, the neutral element. Okay, so the theorem is still not over. So then there exists a unique groupoid homomorphism say phi from Birmori X to G such that if chi is in Birmori X, so such that if you have a birational map in Birmori X that induces phi in Birmori S, then we have that phi of chi is equal to eta of phi. Okay, this is the end of the theorem. So the theorem goes up to here. Okay, so what does the theorem say? So it gives the existence of some integer g. And so later on, so when I said large covering genus gonality, what I meant is that, I meant that g is larger than this integer there. But this integer, it is not explicit. Okay. So this also means that actually, yeah, I mean, so I can't give you, for example, any explicit birational map that lies in the kernel of such a group homomorphism that we construct. Just because I don't know what the G is. Okay, so it means that we have some G, and so now we have that now whenever we have a groupoid homomorphism on the generic fiber that works like as we want, then we get the groupoid homomorphism in higher dimensions. So I made this assumption that the generic fiber is not birational to a conic bundle. So I make this assumption so that again I can control relations. Okay? Because so if we have a large covering genus, we know that the base of the rank 3 vibration has the same dimension as the base of the link. Okay? But a priori, it could be that some of the other links involved in this rank 3 vibration, such that they are over a base of a higher dimension. Okay, so this could be, a priori, you have such cases. But now me with the assumption that we're not birational to a conic bundle, we don't have to care about such relations. So we have that whenever we have an elementary relation, all the Sarkisov links that are involved, all of their bases are equidimensional. So now, then it's still not over to understand all the relations, because I mean such relations exist, but we just have to go through some cases and we can describe all such relations. Yes. Yeah. So actually, I mean a rank 2 vibration over a curve. So now S is a surface. So, and I speak about that S is not birational to a conic bundle. Okay, and now so let's look at the examples that we have. So Blanc-Jasinski, let's look at their S. Okay, so here they have a Del Pezzo surface, so they have cubic surfaces. Okay. So now is this cubic surface, is it birational to a conic bundle? So it is not. Because, so this is a minimal cubic surface, and now what I can do is I can blow up a point of degree 1, for example. So, right, because if it is birational to a conic bundle, it means that there exists a sequence of Sarkisov links that connects the two. So let's look at the Sarkisov links that start at this cubic surface. If I blow up a point, I get Del Pezzo of degree 2. But now Del Pezzo of degree 2, they have the Geyser involution. And so this, and then the link that you get, this will be going back to a minimal, well, goes back to itself. So there is no, so this doesn't give you a conic bundle. And if you blow up a point of degree 2, this is exactly what you get. So also with this link, you don't get a conic bundle. So in this case here, this minimal cubic surface is not birational to any conic bundle. And also with the Severi-Brauer surfaces, so I mean, we looked at all the links that start at the Severi-Brauer surface, right? And in the cases, and in all cases, we go back to some Severi-Brauer surface. So also in this way, we don't get a conic bundle. So here, so in both these constructions, they are in this setting of not birational to a conic bundle. So it could also be, so if you, so there is a bit more involved. I don't think you have directly what you say. So, okay, basically, okay, so one has to look at all, so we have a link, okay, so we have our favorite link of type 2 with all such nice assumptions. Now we need to check all the relations in which it appears. So this means we take some other Sarkisov link and we assume that they are dominated by the same rank 3 vibration. And so we go through all of the cases, so links of type 1, 2, 3, 4. And so in each, so if the other link is of type 1, 3, 4, so not 2, 1, 3, 4, then in fact it is almost always you will get a square relation. And in this square relation, so you have two opposite ones, which are links of type 2, and there are the links of type 1, 3, or, okay, so it depends a bit on what you have exactly. What do I want to say? And yeah, and so then there is like one gets like an equivalence of these other two links, so that it's in the good way. So if you go around this way, then this one here is equivalent to this. So if I do this, then to this one. So that's really like when you do the group Poit homomorphism, when you plug in the relations, you really get 0. Yeah, okay, sorry. Yeah. Okay, so I think I will stop here to make up for yesterday.
Any questions for Julia? I have one. So for the type 2, I understand where you send them with Birmori S, but for the type 1, 3, and 4, do you just kill them?
I just kill them.
Okay.
Yeah, so the links that I mentioned here, I don't know where, but for example here, like every other link is sent onto 0. Okay. And every isomorphism of Mori fiber spaces is sent onto 0.
Okay. I'm talking about for the one with X. So.
Yes, so, okay, yeah. So here you mean, right? So here also Mori fiber spaces are sent onto 0. Isomorphism of Mori fiber spaces are sent onto 0.
Okay.
Maybe I should write this down. And iso of Mori fiber spaces. Tends to 0.
Other questions?
Let's go for lunch.
Yeah, let's go for lunch. Thank you, Julia.